3, 2, 1, go.
Oh, okay. All right. Thank you, Mr. Chairperson. uh, First of all, thanks to everybody who joined this group meeting session. Today, it's my turn. It's supposed to be my turn long time ago. I'm going to talk on the method of factorization, specifically on Morse potentials. But before going into the second part, actually, I tried to work out for the method of factorizations in terms of harmonic oscillator, but let's see how. So these are more or less the outline of my presentation. A bit of a history, and then how we work out the Morse potentials, looking at the least eigenvalue, at least using the factorization method, and then other things. So for the highlights, as I post in the announcement, so we are going to discuss a simple exercise on the method of factorizations due to Morse potential, show the least energy of its Hamiltonian, and then second part of the talk, we're going to look at the effect of non-commutative property on the energy eigenstate of Morse potentials, but specifically in the harmonic limit, okay? Why I'm going to also discuss the second part, because we're going to use all this algebraic form. So the specific highlights are given in the following, 1, 2, and 3. Talking a bit of history, so there are at least over here 2 important parts. So the first would be on factorization method. So this will be the work by Infeld and Hall in 1951. So published in Review of Modern Physics. They called, so the title is the factorization method. So over here, Hall and Infeld discussed there are at least 6 types of factorization method. Okay. Not only that, we talking about recent development on factorization methods, we can find one, but there are more at least. In this paper, 2019, so they have a deep rational matrix factorizations method for recommendations large-scale sparse data set, okay? Apart from that, the one that I'm going to present here is taken from matrix mechanic by Green. Okay. We move on for Morse potentials. Okay, Morse potentials begin with the work by P.M. Morse in 1929, where he discussed diatomic molecules according to the wave mechanics too. Okay, talking about vibrational levels, so or vibrational energy. And then other current or recent on Morse is given in terms of we can find more, but mostly according to number three is in terms of modified Morse. Okay, so we look here, there is Morse potentials looking at different dimensions, high dimensions, and then talking about double Morse potentials, and then we have this so improved modified kind of Morse potentials, Rosen Morse, and so on and so forth. And the work on non-commutative theory on Morse potentials, there's not a lot, so that's why we are interested to look at them. Okay. For factorization method, if we want to take the correct definitions, is an operational procedure which enables us to answer in a direct manner questions about eigenvalue problem, which are of importance to physics. Okay, so in general, we are going to deal with the eigenvalue equations. All right. So these are the papers of Hall, and there's another good books on factorization method in quantum mechanics by Shi Haidong. Okay, published by Springer. So if you look at there, so it's probably algebraic, and there is Lie algebra discussions among here. So if you look at part 3 of these books, there are actually quite detailed workout or solutions into applications in non-relativistic quantum mechanics. There are also applications in relativistic QM, but so the potentials that you can see here, starting from harmonic, infinitely deep square, we have Morse depth, partial Taylor, pseudo-harmonic, and so on and so forth. Okay.
Can I interrupt?
Yes. You can interrupt anytime.
Are they doing one-dimensional or the two?
They are doing one-dimensional. For this one-dimensional. And then there's also this position-dependent Schrödinger equations. Okay. So this is a paper by Morse. Okay, I just step here and I want to highlight these are the energy eigenvalue for Morse potential. So you have En. So usually this En here, E subscript with here is the constant energy. Okay, I will talk about it down below how you reform your Morse potential. Okay. So again, if you want to interrupt me anytime, you can do that. So let's move on to Morse potential. So in one-dimensional Morse potentials is given by equation 1. So this is, I should have put source here. It's from Wiki. So you can compare here from harmonic and Morse potentials, the green one, harmonic potentials, and then Morse potentials. So you have the bound states of these two potentials by right. So dE there is the well depth, okay, and D naught due to the association distance between the 0th point. So in most potentials, you do have the unbound states by right, okay. And then usually these potentials is in R parameter. So R will be your distance between atoms. And then you have another parameter, alpha, which control the depth. And you have the RE, the equilibrium bond distance. So usually we can start with equation 1, but you can expand equation 1, all right? And then you can reform such that you want to choose a separated atoms limit as the 0 of the energy for which you want to study zero order approximation. Then eventually, usually most papers will discuss your Morse potentials in the form of equation 2, okay? So you can do some change of variables in terms of the distance. Instead of R, now you're using your X over here. And then, so you're usually instead of V naught, this is equivalent to your DE, okay, scaling energy constants. I did not put what X equal here, but you will be clear afterwards what it means, okay, what it looks like. So let's move on in general what's factorization method is, okay, so suppose we give a set of numbers here, eta 1, 2, and eta n. And then we want to determine the operator f, or you can rename this, redefine f1, such that you are taking this n1 dagger, n1 plus n1, plus some f, okay? In which f1 here is the physical number that has the maximum value possible for representation number 3, representation 3. So another definitions, you can also have F2, okay, equivalent to that, or you can put F2 with a different strict order, okay? But there are some constraints to this. So your F1, your physical number, F2 must be larger than F1. So you might need to have like an increasing, increasing in terms of the operator. So according to this scenario, you can have up to n operator, and you can write either this part or the other part, okay? So if you introduce a vector now, let's say your phi n, cat phi n, then it would be like this. And then again, your cat phi is your normalized eigenvector of operator f belonging to eigenvalue f, okay? So you can write your eigen equations like the following. So remember this is to solve eigenvalue problems, okay? So this is definitely your eigenvalue equations. And again, it's normalized. And then you can find such that at least for the first term, so you can rearrange such that find the inner product between these two, the first vector. So how you get this, actually you are using the relations from number 3, and then eventually you can write the inner product is given by that. So this F, of course, from the eigenvalue of your F, a big F, okay? So it follows that your F must be larger than the first F1 from the fact that your inner product must be larger or equal to 0. So in the same manner, you can also find the inner product up to n vectors. Using the fact of that, then you can find your F is much larger than each of your Fn. Okay, but the general idea would be the following. So you want to identify that quantity F is either more than each physical number of that Fn or equal to one of them. So these quantities which are represented in order of increasing magnitude will constitute the eigenvalues of operator F. So this is from equation 3. So usually the sort eigenvalues are represented by En equals to Fn plus 1. So note that the constructions of your eigenvectors, exact solutions of your operator F, can also be worked out in an algebraic manner. So I suggest you can look at this particular literature, but we are not going to discuss it here, okay? So we leave out the eigenvectors first, just concentrating on the eigenvalues. All right, so now let's move on to Morse potentials. So there are, in general, you might not see it, what happens here because it's how it works. So for Morse potential, it's actually a potentials involving anharmonicity. So I think this is favorites among all. So we always have this Hamiltonian. So you have PR there in terms of given momentum, so kinetic energy plus your potential energy. Okay, so this is what I said, your X that correspond to your Morse potential area will take this form. So R minus RE over RE. Okay, the RE, this is, so RE here is actually your R naught. Okay, this is typo. So your RE is the equilibrium value. All right, so next is the scheme to determine the eigenvalues. So given VR, okay, so now you can have Vx there. So once you do that, so your Hamiltonian is given by this again, and we postulate such that your F, so that you're focusing on trying to find the operator F now, is given by 2mh bar. This is just for the sake of trying to make your calculations more simple. So you multiply by 2mh, but at the end, eventually you have to divide by 1 over 2m. Okay, so what happens from 6, if you expand 6, okay, expands mean you multiple twice all the details in the bracket, and you can arrive at equation 8. Okay, so for which your A here, the Morse parameter will involve 2mv naught. Okay, and then we're going to choose the Q numbers, the numbers, eta n. So we choose that we have the eta n and eta n plus. And then we choose in the manner that you have the PR plus I, Bn, Cn with this form. And for the plus, it's like a conjugate, okay? And it's always like that. And Bn and Cn here are the real quantities, okay? So the explicit forms of which are to be defined. So we're going to find what Bn and Cn specifically. At the end, we can find your operator. Okay, so we calculate. So remember the term you always want to calculate n, this eta n plus eta n. Okay, so we expand that and notice that because we deal with momentum and position, we must be very careful. So they are non-commutative. But look at here when your PR is in terms of like that, but your X in terms of R minus R over R naught, R minus RE over RE, okay? So forgive me here again, it's a typo there. So it's not a good way here because one is X, one is R. I think you know what happens, okay? So once you get that, yes?
Your momenta is the, what you call, the ordinary momentum.
Yes, the ordinary momentum. Correct.
So only X is going to be dimensionless.
Yes.
Okay.
Okay. So yeah, it's a mixture here. It's very bad. Okay, so students, please. Okay, so but you know that your x is in terms of, let me remind you again, your x is this part. Okay, so maybe I should put x bracket r, which must be proper. All right. So once you do that, again, must be very careful handling this commutative bracket. And then what you do, you just put the answer, what you get inside number 9. So you arrive at equation 10. So in analogous manner, you can also find eta n plus, but this will be give you in terms of a different sign. Okay. So what follows here, you have Bn terms, the terms of the Bn and Cn. It's like the coefficients, okay? So now we are considering the operator, like the one that we have earlier. So F1, operator 1 with eta 1 plus eta 1 plus F1. So what you do is, okay, you take whatever you have or whatever you have calculated before for eta 1 plus eta 1, which is this form, and you add them up with these additional terms, F1. And remember, from the other side, we also have this operator, okay, for which we defined earlier F1, which we postulate earlier. So we also have this form. So next, what we do is we are comparing like terms. So in the way that we want to find at least what is B1 and C1 and their relations. So we have like 3 sets of equations here. So C1 square equals to A. So comparing like terms, you see, so whenever you look at at least the last terms here, so for which you multiply a factor of exponential minus 2 alpha x, then it's equivalent to that. So you arrive at this part, okay? So C1 square equals to A, then you have another one, pure constants, which is A, and then you have another one, which is multiplications of that, and make it equal, all right? And you can rearrange. You can also have relationship of B1 and C1 at least at this point. But at this form, you have to be critical about what a value that you can take. Okay, so C1 here would give you a plus minus square root of A. So there might be 2 possible solutions. One is minus of that, and the other one is positive. So you can write both for B1, so you can find out the exact form of at least B1 and F1, similarly for the other case. But we have some constraint there, then we choose the case of F1 is greater, that is, we are looking at this form. So we are choosing for your C1 in terms of positive of your square root A. All right. Just to make things even simpler, so this is suggestions from the book. I take from the one that I suggest earlier. So you can rearrange such that in some manipulations of h bar omega, okay, you can write in terms of all the parameter involving Morse, okay, in which omega here will be your vibrational frequency, okay, and your lambda here is correspond to one of your RE, okay, RE here, the equilibrium state distance. Then you can write your alpha in terms of all the known parameter. And then consequently, after you have, you define those, then you can write your F1. So the F1 is the following, having alpha square root A. It's given by this, okay? So this might be more well known to you, okay? So note that you are looking at the least energy here, the least Hamiltonian, so it will be your ground state. So E naught, then your E naught is actually just, it's expressible as your F1 over 2m. Okay, so because of this 2m you postulated earlier, so what you do, you just divide by 2. Okay, so then you have h bar omega over 2 minus h bar omega square over 16d. All right, and remember this omega again is your vibrational frequency. Compared to the one that has been proposed by Morse, so Morse have additional term, EE, so that is because they didn't take out the constant term of the potential. So, but if in this case, if you're putting your n as equals to 0, then you get your least energy. Okay. But for other eigenvalues, okay, so one need to look at the comparison of the two expressions for F1. Okay, this is a bit lengthy actually. Okay, but I do the most simple things in terms of harmonic oscillator. Okay, but for the other eigenvalues, what you can see, but in my abstract, I just want to focus on the least Hamiltonian. Okay, but for other eigenvalues, you have to compare two expressions. One which is your operator of n+1, and the other one is for operator of Fn. Okay, so once you compare them, and compute the eta n plus eta n, and then the other side will be eta n+1 plus eta n+1, and then you rearrange such that, so follow the same technique, same rules, you will arrive at this form. Okay, and then at the end, your eigenvalues will be expressible by your En equals to Fn+1 over 2m. All right. So let's try to look at harmonic oscillator. Okay, so I tried to find a harmonic oscillator in some way in other literature. They never discuss it. Maybe it's too obvious. I'm not sure, but when I tried to do it, take some time. Okay, so for harmonic oscillator case, you have equation 12. All right, so I just take this one dimension. So your momentum will be the usual momentum in terms of x directions, and then again follow the same technique. We postulate you have that, and eventually you take out this. Okay, and notice that we want to find the numbers eta n and eta n plus. Oh, sorry, it should be eta n here. So in a way, I choose the following. Okay, so that for a given operator, you have this expression. Okay, F1 eta 1 plus eta 1 plus F1. Then the lowest energy would be F1 over 2m. So what we are going to do next, again, we are comparing. So we do that for the first term here, you have that. Okay, so you have A1. So you have to find, you see, an. Okay, you have to find a specific value of an. So once you do that, you have again there is some commutative bracket involved. Okay, so that's why you have this h bar a1. Okay, and then plus f1. So compare this with the other part, comparing like terms again. So you see that your a1 square is equals to your m square omega square, and eventually your a1 is this m omega. So again, your F1 is actually H bar. So this is a tricky part, okay? Because actually you have a minus sign there. Actually, if you have F1, this part, these two terms must be equal to 0 by right? So you have minus H bar A1 like that terms. But the least eigenvalue, you have that. It should work, but you have to be careful with that. Actually, if I take n plus, is that n plus, I have a minus sign here, okay? So if a minus sign is here, then you get it correct. The way that I do it for other eigenvalues, okay? So for other eigenvalues, I compare with Fn and Fn plus 1, so both sides. So you notice that we can obtain in such a way, you can do the comparing like terms. So eventually, again, your n is an squared, okay? At least it's equals to that. So for a maximum value of m or f1, your a1 is equal to m omega. But next, you're comparing the terms of these two terms, all right? But we have to do the following. I try this out, okay? And you're summing these two equations, all the one that you have, and I try to come up with this part, and at the end, you have the other terms which give you this, okay? And then eventually, you want to compute your En, that will be your Fn plus 1 over 2m. Then you get back your energy eigenvalue for harmonic oscillator, okay? All right. So question?
Yeah, why are you redoing the harmonic oscillator case?
Oh, okay, because never found anything from the literature.
Okay.
So I want to make sure it works.
So essentially, it's just the ordinary harmonic oscillator done in a generalized recursion kind of.
Yes, recursion relations, correct. Okay. Is it okay?
Go on.
All right. Okay, so then we go into the next part of the talk. So I guess this part is just purely algebraic manner, okay? So Morse in NCQM. So just a brief on NCQM, I think I really know what I'm doing, okay? So we are focusing on equation 15 here. So there are comparing a CCR from 14 and 15. So if we are doing an NCQM, then we have these additional terms, okay? Just a bit on physical interpretations and applications. So I highlight again, so Morse potentials, we are looking at the vibrational states and energies, okay? So study of molecular spectra and NCQM. So usually we are trying to compare your theta, which is your NC parameter, with H bar, okay? But to combine these Morse potentials and NCQM, well, the most I think the usual NCQM works pretty much okay is in terms of a harmonic oscillator. So Morse potential, because it's in terms of unharmonicity, so it causes a lot of things, okay? But the usual way, so this is how you redesign your Hamiltonian in terms of calculus, okay? Differential form. And usually people would take, researcher would take some change of variables, y here, okay, and then you rewrite your Hamiltonians in terms of mu and s, okay. So we are looking at, again, the operator method here, okay, specifically at creations and annihilations. So this will be like your n plus and n, eta plus and eta. But the nice things is we can have Morse potentials in harmonic limit, for which we have this B dagger, B dash. Okay, this is from this book again. So you can have it similar like your A dagger A, for which their commutator equals to 1. But then nice things over here in these harmonic limits, you have the extra parameter of alpha and nu, for which alpha here that is correspond to the Morse parameter. Okay, so we can say something about it. All right. So how is it related to energy? This is just some revisited. Okay, so if you can write your Hamiltonian like this, it's eventually you can find your energy. So if you have some features or additional term or shifted, then you can say something about the energy. Okay, that is the case. All right. So we are going to look at the associated Bob shift. We call it Bob shift, but Tisha might not like it. Bob shift this. Combining Morse potentials and NCQM. So we introduce here deformed operators for Morse potentials into dimensions such that, of course, we are doing this in the harmonic limit relation, okay? So such that we have these Q1 and Q2 as the following. So first we work out, we take your momentum is commute, okay? So we check commutations relations, for which this is correspond to what we done earlier and the one that we have here. Okay, for which we are translating CCR based only on your position that is non-commute. Okay, so this is what we have. Okay, the deform according to Morse potentials. So for deform operators, okay, once since we have this analogous to your ordinary destruction and creation operator, we have the Hamiltonian since in 2 dimensions. Okay. So in some conveniently chosen units associated to your Landau levels, okay? So so we don't have all the M, all the additional there, physical constant. So we substitute the one that we defined earlier from 20 and 21, okay? Substitute in 23, and then you arrive at your Hamiltonian of Morse, but in non-commutative space, okay? Space because of only positions non-commute. All right. You can deform further. Okay. So you can further. Yes.
Equation 24.
Okay.
The combination is px and y and py and x.
Yes.
Okay.
Okay.
Hello, Dr. Nurisya.
Yes.
Fauzi here.
Okay.
Actually, according to equation number 23, so far that I know, there is no Morse potential there in equation 23.
Oh, okay. I take this into account after you see we are looking at the harmonic limits. So it works well with the harmonic oscillator part, see, where we deal with that, then we can produce such.
And then where is the explanation from Vinish?
Oh, like I said, this is in terms of harmonic limit. So we're taking the parameter in terms of exponential very large.
Meaning
So,
that you expand the exponential.
yes,
Oh,
yes,
okay.
yes.
Okay.
Specific for harmonic limit. Okay. So can I continue? Yes.
So this is like a lambda.
Yes.
Okay.
Correct. Once we go there, okay, you can further simplify. Okay, so some algebraic manipulations there, and then you can letting gamma over this form, okay, parameter, and you introduce the following operators, okay. So now we are looking at both Q and P non-commute, okay. So Q1 is like that, and your P1 is the following, okay, and then you can rewrite your previous Hamiltonian in your 24 such that you have in terms of 26. Okay. All right. So you have additional terms of gamma there. All right. So this final form is simply simply a generalized Hamiltonian for your Morse potentials in harmonic limit. Okay. So what we are going to say about this is, okay, if you look at the final form of your Hamiltonian in the case of a non-commutative phase space. Okay, so now you see your P1 is not really Px. Okay, it's deformed. Okay, so you saw that you have this part. Okay, so you can write, if you write everything in terms of P1 hat and Q1 hat. Okay, in terms of Q1 hat, P1 hat. So you notice that there is some shifted there. Okay. And then once if we equate, then you notice that there are some shifted of energy levels in terms of these terms. Okay, theta over 2 alpha multiplied with square root mu. Okay. So and then these shifted energy levels will correspond to Morse potentials in NCPS, non-commutative phase space. So the effect or the shifted energy is given by equation 29. All right. Okay, so you see, supposedly if it's commute, we don't have that terms, but now we do have some terms, additional terms there. Okay. Then that's the end of the talk. All right.
When you say non-commutative phase space, but you consider the axis that.
Yes. So you see, previously, if I go back here, so if you first here I introduced Q1, Q2, uppercase Q1, Q2, but I maintain P1, P2 as just Px, Py. So once you have that, so you put in the Hamiltonian correspond to the things, and then you see your P1 is eventually your Px. Okay, but you can rearrange or factorize whenever necessary. So you arrive at 24. So next, if you're introducing one alpha there, gamma there, so you can form your Q1 hat now with P1 hat in parameterized by this gamma. So now
Dr. Why Q1 and P1 respectively not same? I mean Q1 is supposed to be X, right? I mean equation 25.
Which one? 25?
25, yeah.
Okay.
But then Q1 should be X and then followed by X Py lah. And then for the P1 should be start from the Px and then followed by Py lah, X
Yeah, it's the other way. You know that the terms is different. Yeah, it's X. They are always combinations of X and Py or Y or Px.
Oh, okay.
So in
Okay.
other words, there's only one set of Q.
Ah, yes, you're right.
Oh, meaning that you just talking about the Q1 only, and then Q2 is
Yes,
Q2
yes,
equal
yes.
to Q2 lah.
This only
Oh.
Q1 only and P1. Yes, correct,
Um,
correct, Doctor. So it turns out that we can find such.
and then again, your topic is about the factorization method. Why don't use
Okay.
ladder operator lah to develop the what we call it state lah, according to the Fock space,
Oh, okay.
and then you can
Ladder
solve the problem
operator.
using the ladder operator.
Actually, I'm taking the ladder operator info, but then it's ladder operator, by right?
Yeah, yeah,
With
ladder.
my P1, yeah, yeah.
And then you can replace the equation 23 to the what we call it in the ladder operator, and then after that you can solve on the Fock space. Oh
I
yeah.
don't think I get you. Oh, okay. Can someone rephrase that, or can you rephrase that? You mean you want to build up the states with ladder operator? Over here, I just want to say something.
Because the solution, I mean the final solution of your presentation here is shifted energy equation.
Oh, okay, yeah, shifted energy, but trying to focus on solving the Hamiltonian part
Yeah.
with that operator.
So shifted energy here means
Shifted energy
how
here,
much energy to convert from the commutative to non-commutative, right? Is it?
well, this is the shifted terms. So you see, without this second term from equation 28, you have the usual form of a Hamiltonian, right? Which
Oh,
give you energy. But now you have additional terms, so this is what we say that
okay.
there is a shifted in terms of the energy.
Oh, okay.
But if correspond to
So let me get this right. So
okay.
begin with some kind of 2D Morse oscillator system, right?
Yes, 2D Morse oscillator system.
In the harmonic limit, and then you generalize the operators. But in the end, you end up with one set of Q and one set of P.
Oh yeah. Yes.
So how does bit confused on that?
So at the end, this part trying to show that okay at the end. So you're trying to say that I should have another Q2 and
Well, I mean,
P2.
you had essentially in the beginning, Barat, you have a 4D,
Yes.
right?
Yes.
So now
Yes.
you made the combination in such a way that you reduce it to an supposedly an equivalent 2D phase space.
Yes. But you see, we're still working on. If you look at 25, we still have like 2D. Yeah.
Yeah,
Yes.
yeah, but how is that? How does that work? Huh? D phase space.
That's a very good questions.
Unless you do some kind of some nonlinear trick.
Sorry. What metrics?
No, something nonlinear about the transformation.
Oh, nonlinear in terms of the transformation, you're saying?
Yeah.
I think there is something anti-symmetric over there. I mean, you can I don't know, because Q1 you have you have the equation, and then Q2 you also
Oh,
have
okay,
the
maybe
worksheets.
yeah.
Oh no, just my suggestion.
So Q1 is summation, P1 is summation.
Oh yes. Oh, did I miss any minus sign there? Let me put it back. Maybe I should calculate this back. I think I have a minus sign, right?
Yeah, betul, right. Because Q and
Yeah.
P is
Instead
inverse each
plus
other.
minus.
Yeah.
Sorry. Should
Mm.
have a minus sign there. Yeah. It's minus sign.
So
Yeah, let me think of this. You're talking about this non-linear. Is it what
Because
you call it?
I'm a bit confused about the way you met from a 4D phase space to a 2D phase space.
Yeah, 4D phase space.
No, something something which I have not seen before. So
Well, we did this earlier with a harmonic oscillator things.
okay,
Yeah, this is in my PhD
your
thesis.
okay.
But we never discussed about this looking at transforming 4D phase space to 2D phase space. So that's why I tried it on Morse on the harmonic limit type.
So this is quite unlike the ordinary NCQM, right?
Yeah, yes. At this point, actually, last time we're just trying to show that the difference between taking non-commit between position and also non-commit between both coordinates. Okay. Anyone else? Any comments or no questions?
I guess that's what do you call it? The title is typo. Right?
Typo?
That is a shift, not shifted energy.
Oh, okay. Typo title, shifted energy levels? Oh, in the... Oh, where is it? Oh, yeah, yes. Thank you.
Okay, that's
Okay.
new.
Now
That's...
everything has to be made sure because yeah, right.
Okay, that's a good comment. Thank you, Azazi. Yeah, it's very... All right. Okay.
So can we generalize this in terms of more, I mean, bigger system compared to this?
So sorry, you are too far.
Can we generalize this result?
Generalize?
I mean, I know how to formulate the question.
You want to generalize what result? This result?
Yeah, I mean,
I'm not sure. I'm not
it's
sure.
okay.
It's possible. Okay, does Hisham have something else?
No. Can you just remind us what you did for your PhD? So same thing, right? Sorry.
Yeah,
Because
same.
I
Yeah, same
totally
thing.
forgot. So in other words, in your PhD thesis, you are doing also a 4D phase space, and then you do some kind of transformation, and
Yes, this part actually to cover. Okay, my reviewer referee last time they want some more physical results. Okay. So Prof. Tariq suggests, Nurisya, I think you better prepare more like, okay, you can show Hamiltonian with energy. So we come up with this. So we come up with this part.
so it's again 4D to 2D.
Yeah.
And your generalized Hermite polynomial is coming from
No. My generalized polynomial coming from for
4D.
4D.
Okay, then. Okay.
This from this part. No, okay. See, these are just okay. If it's we're talking about physical, then we want to say about some different or deformed energy, but we never talk about the states. We never discuss further on the states. So maybe good questions from Ahmad if you want to generalize or you want to do more than trying to look at the states, perhaps.
Mana tukar bidang.
I don't want to generalize. I just asking.
I mean, not generalize. You can put up more works to it, but we never go into the states part because I think we better look at the 4D phase space with higher dimensions, like 3-dimensional things. Not this. Okay.
Okay, Fauzi is here. Okay. Okay. Actually, why Dr. Nurisha not solve the Morse potential itself? I mean, why you apply the limit? Because according to paper Shi Hadong, uh,
Yeah.
he used ladder operator to solve the problem.
Yes, but we can we can have a deformations. I think Nadira have presented this for the most potential part. The deformation of the operator is with
because
the exponential part. It's non-linear. Okay, it's difficult to have a combinations of your bob shift in exponential.
uh,
That's
because
that's that's the problem.
because I'm very awkward about the paper. I'm really interesting about the paper because he consider the exponent x
Yes, for
as a
the
SS, and then from that base we can develop the board shift, and then we
But if you notice somehow, if let's say you start with your Morse potentials, usually when we impose the bob shift, okay, you
mhm,
substitute your bob shift into your Hamiltonian. But if you have an exponential part in your Hamiltonian, then you have a combinations of x and
mhm,
momentum in terms of
yeah.
Hamiltonian. So how are you going to I found it difficult to work that part unless you just play around with the already well-known ladder operator for Morse. Okay, but if you want to develop like what you did in a harmonic oscillator, so you do the substitutions of bob shift properly, I think it's difficult because most potentials have this exponential. It's a non-linear kind of potential.
Because they develop they treat exponent x as the position, so that's why
Ah,
they can
yeah,
develop
yeah,
the ladder operator.
yes. But I tried out before. Y1, Y2, but something funny, yeah.
Oh,
But I do have. I think Nadira have something to say about it. We work on that as well on the operator side for Morse, exact Morse, not in harmonic limit.
yeah.
Mm.
Because this one you reduce to,
Yes,
you
yes,
apply the limit and then of course we be
yes.
back to the apa, harmonic oscillator. Okay.
Okay,
Okay, should I stop recording now or?
okay. I stopped recording as well.